The final practice problem from section 12.2 on vectors is number 14. And it's an unusual question in that it asks us to do a proof, and I can think of a visual proof for this, so I won't do it analytically, although I'm sure there are good analytical proofs that exist. Basically, the premise is this. We have two non-parallel vectors, A and B, so I just drew two vectors that point in different directions. Finally, take a third sort of random vector, C, and again, I just drew this vector, so none of these three were measured or figured out in any particular way. And what I want to try and prove is that with the proper selection of scalars, one to multiply by A and the other one to multiply by B, I can make the following equation true. I can make the equation that C will actually equal S times A plus T times B. And it's the fact that there are suitable constants S and T such that this can be made to be true as long as A and B don't lie in the same direction. If they do, then it's going to be impossible to form C out of some combination of them. But as long as they don't lie in the same direction, there are always suitable choices for S and T. Let me show you how it works. First, we're going to start by reconstructing C. And then from the end of C, I'm going to start right here, I'm going to draw a vector that runs in the direction of A. So there's the direction of A roughly, and I'm actually going to draw A right on top of it. So there's vector A. Now, of course, vector A won't be long enough to do what I want, but remember, we're going to multiply A by some sufficient coefficient. The next thing I want to do is draw in vector B from somewhere along the direction of A so that it points towards the other endpoint of C. So let's do that. Let's figure out where I would need to put it. B sort of points in this direction, so it would have to be somewhere around here would be vector B, and then again I want to sort of extend that line so it carries all the way through. So here's vector B. Well, now we can see the visual proof has been achieved. A isn't the right length to reach to this point, but if I multiply it by an appropriate coefficient, let's say S, and S is exactly the right length to make AS long enough to reach this point right there. Why is that point so magical? Well, if B starts there and points directly towards the other endpoint of C, then the appropriate choice of T will extend B's length until it reaches that endpoint. Therefore, SA plus BT will perfectly form the vector C. And that basically is how we conclude the visual proof, that there's an appropriate choice of S and T in order to make this vector equation true, as long as A and B don't lie on a line. If they lie on a line, of course, there's no way to get from here to there if they both pointed in this direction. Now, you might wonder what would happen if A and B pointed in the other directions, if they pointed up instead of down. That is, if A, instead of pointing up and to the right, suppose it pointed down and to the right. Well, then I would put A here. And suppose B also sort of pointed off to the left. Well, then T would have to be a negative number to flip it over. So you can see no matter what combination of A and B, as long as they don't lie on a line together with C, then it's very, very possible to build this visual proof.